Hello everyone. Today we are going to discuss the section 16.3. It's on fundamental theorem for line integrals. This is the last week of classes for spring 2020. So I hope you're doing good, you're safe, and you're ready to take the final exam. And let's do this, okay? So what we're going to do in this section is remember the calculus 1, calculus 1, the fundamental theorem of calculus. In that, I think you had a theorem which says integral a to b f prime of x or like how do I say f prime of x dx is going to be derivative and the integral and the derivative signs cancel out, so upon substituting the limits you get fb minus fa. Roughly this is what the theorem was. The notation might be slightly different, but this is what it is. The fundamental theorem of calculus, you studied two of them. One of them is to evaluate the definite integral. The second one is to show that the derivatives and integrals are opposite processes. So that's a bridge between the derivatives chapters and the integral chapter. Okay, so if you have the integral of the derivative, they just cancel out and you just get the function out, and upon substituting the limits you get fb minus fa. So similarly, do we have a theorem in Calc 3, that means for a function of multivariables, and that is where all this is coming across. Remember in section 16.1 where you studied vector fields, you said one was a potential function which is a scalar valued function, the other is a conservative vector field, and then in 16.2 you talked about the line integrals. And remember, line integrals depends on the direction or on the path. If you take different paths you might get different answers, but when you talk about a conservative vector field, it only depends on the endpoints, and there are several ways to evaluate the line integrals. All that you studied that. So in this thing, we are going to 16.3 is on fundamental theorem for line integrals. In other words, it is very parallel to the calculus 1 fundamental theorem. So in calculus 3, remember you did not have any fundamental theorem of calculus in calc 2. So in functions of multivariables, what they are saying is if you have an integral over entire interval over c, that means here it starts from r of a to r of b, then you have gradient f dr. That's a line integral. It's like the gradient and the integral, they cancel out, and what you get is upon substituting the limits you get f of rb minus f of r of a. Okay, that's what it is. I will hopefully show you the working on it, but that is what it is. Let C be a smooth curve. Smooth curve means you would be able to find the derivatives. Smooth continuous means you can draw the graph without taking the pen off the paper. That's a very layman definition. Smooth means at every point you are able to define the derivative, and your vector function is from r of t, which is a to b. In this case, otherwise you can write this as integral over c gradient of f dot r prime of t, and you have dt, that is going to be f of r of b minus f of r of a. Okay, so this is what is the fundamental theorem of calculus. Now how did this come about? Do I have a place to prove this? Let me see that. Do I have a place to prove that? No, I don't have a place to prove that, so let me show you briefly what happened. Now if you have integral over c gradient f dot dr, so which is going to be integral over c gradient of f dot r prime of t dot dt, so which is going to be a gradient is going to be, okay, it's a vector, you get fx, fy, fz. I'm considering function of three variables, and dot r prime is going to be x prime, y prime, z prime, and dot dt, where your limits are going to be on the curve c but because we moved from dr to dt, this is going to be from a to b, because remember your function when you are in the variable t, it is from a to b. When you are in the along the curve, then it will be out of a to out of b. Okay, so this is going to be a to b. So this is going to be integral a to b fx times x prime plus you get fy times y prime times y prime plus you get fz times v prime times v prime, and you get dt here. Okay, then what happens is upon integrating you get a to b, you got partial f partial x times dx dt plus partial f partial y dy dt plus partial f partial z dz dt and you get dt. Now you should never say this loud, but if it's like the x's gets cancelled out, the y's gets cancelled out, the z's gets cancelled out, but you should never say that. Okay, so that's going to be integral a to b. This is a chain rule. If you see that, this is nothing but the chain rule, and it is a chain rule for what? It is a chain rule for d by dt of f of r of t dt. Now it starts looking like your Calc 1 fundamental theorem. So the derivatives in the integrals get cancelled out, so you get the function back, so you get f of r of b minus f of r of a. Okay, so that's what this is. That clear? So the line integral of the gradient dot product with dr will give you f of rb minus f of ra. Remember that. That's the fundamental theorem of calculus. Now f dot dr is independent of path in D if this is equal to 0 for every closed path C in D. So what does that mean? So closed path means this is closed. That means the terminal point and the initial point are the same. Closed point is like this. I mean, you know, but this is closed. This is closed. Okay, this is not closed. I want to tell you that, because I mean the terminal point and the initial point are different. I mean, you know, you don't have to have circles, but you can have any weird shape like that, and then that's closed. This is closed. Are you with me on that? So if you see that, what happens is if you have f dot dr, so if it is a conservative line integral, that means this is a conservative vector field. That means you can find the potential function dot dr over the C. So which means this is gonna be f of r of b minus f of r of a, which is gonna be, this is from section 16.1. I explained it in my video, and this is like fundamental theorem of calculus for line integrals, which I just explained in the previous slide. Now if a equals b, this is 0 if a equals b. In other words, a equals b means what is that? It means that the path is closed. That means path is closed. That means you have initial point is equal to the same as the terminal point. I mean, wherever it is that. Okay. So now so that's what we are using right now. Okay, so if the line integral over a closed path is 0, then you can say that the line integral is independent of the path. Okay, then let's see what the next slide is. Suppose f is a vector field and is continuous on an open connected region domain D. If C is independent of path, then f is a conservative field and there exists a potential function f. So that's what we are saying, right? So I mean in 16.1 you said in f dot dr we said I mean, you know, you could always find f is gradient of f, so gradient f dot dr, that is like 16.1. F is called the potential function. I want to tell you that potential function, and f is a vector field associated with it, or in other words conservative vector field associated with it, vector field that is conservative, okay, conservative. In other words, if you can find a function f such that gradient of f is equal to this capital F, then this f is said to be conservative vector field. Okay, so then what happens is then there exists then if this is independent of the path, then f is the conservative vector field, and you can find such a function f. So if f is given, can you find gradient f? I mean, you know, always. Answer is yes. For gradient s for f, if f is conservative vector field. No, I can't find f if f is not conservative vector field. I hope you understand that. In other words, if this is a conservative vector field, you can find f. If this is not a conservative vector field, you cannot find such a function, potential function f. In other words, this is like a when can I find the potential function? This is what they're saying. If the line integral is independent of the path in D, and it is a conservative vector field, then it has to be. That means first the domain has to be open and connected, and and this has to be conservative vector field. Now, what is open? Open means, I mean, you know, if I take in, let's not get to open. What is connected? I mean, connected means if you have that, if you take any two things, they are connected. I mean, the whole path lies inside. That's what is connected. But other than that, I mean, if you have something like, let's just say, and there is a puncture here, you have this, so that's connected again. So these are some of the examples of connected vector field. Okay, connected domains. Okay. Then now if f is such a vector field, is conservative vector field only if this is it. So that means, I mean, you know, remember this, f of xy is gonna be here you defined it as p of xy and q of xy. These are the two components. I mean, we are dealing with two in a two-dimensional space. Okay, so that means f is a, remember that it is a conservative vector field. So if that is the case, then you can find a potential function f such that f equals gradient f. And what is gradient f? It is going to be fx and fy, correct? So which means automatically what we are saying is fx is going to be p and fy is going to be q. Remember that. Okay, so you see how I got fx equals p and fy is going to be q, right? Now let's find the mixed partial. So that means if I find fxy, that's going to be py, and if I find fyx, that's going to be qx, right? And but then from Clay-Root's theorem or Clay-Rod's theorem, whichever way you want to say it, by Clay-Root's or by Clay-Rod's theorem, we know that fxy equals fyx, correct? Once that becomes true, that means you get py. By Clay-Root's theorem, py is equal to qx. Do you agree with me enough? So what are we saying? We are saying if f is a conservative vector field, there are a few things happening. One is you can find there is an f such that f equals gradient f. Okay, and f is also the vector field is defined by p and q, and gradient is defined by fx and fy. In addition, because f is a vector field, there is another thing that happens, py equals qx. Okay, this works both ways. So that means if py equals qx, f is a conservative vector field. If f is a conservative vector field, then py equals qx. It works both ways. Okay, I hope you understood it. if you can find the if f is a conservative vector field, you can find a potential function f such that f equals gradient of f, and the gradient of f is nothing but two components in x and y, and the vector field is given by p and q. Setting the components equal and using the Clay-Root theorem, we can get py equals qx. In my head it is clear. I hope my clarity came across well in this video so far. So that's what they are saying. Suppose f is a vector field and open simply connected region D. Suppose that P and Q suppose P and Q have continuous P and Q have continuous first partial derivatives than this. That means if f is conservative, then this is true. If this is true, then f is conservative. That's what they're saying. So f is a conservative vector field implies py equals qx. In other words, if py equals qx, then it implies f is a conservative vector field. I mean, both ways it works. That's what they are really saying here. Okay. Now, open simply connected domain region D. I mean, how do I say? I'm not face to face, so let me just say accept it for now. I mean, I can draw pictures. Okay. Open simply connected region. I mean, some examples are, for example, this is open. Let me make OSCR. This is open simply connected region. But if you have something like this, two circles broken, then this is not open simply connected region. This is not open simply connected region. Or you can have something and you can have a break inside like this, then this is not open simply connected region. I hope that is clear. Okay. Now let's see if something is conservative or not. So here, like this is P, that is Q, right? So you want to find Py. So partial derivative of y with respect to 3 plus 2xy. So derivative of 3 is 0. Derivative of 2xy is a 2x. So that's going to be 2x. And then you have qx as partial derivative with respect to x, so that gives you x squared minus 3y squared. So derivative of x squared is 2x. This is going to be 3y squared has no x in it, so derivative with respect to x is 0, so that's going to be 2x again, right? Are you with me on that? So here you have py is equal to qx, so that means f is a conservative vector field. Remember that. So because it is a conservative vector field, now you should be able to find, I mean, I'm done with the problem, okay, but I'm just saying. So FYI, it is possible to find, f such that, what is that? Such that f equals gradient of f. Okay. So we are not finding it in this problem. Is it a conservative vector field or not? Yes, it is. That's all. In the next question, what is the thing? I mean, you want to find such an f. You see that? So I know that this is P, that is Q, and I also explained that this is fx and this is fy. So let's start it. If for someone who has done differential equations, this is very similar to exact equations. If you see that, that's why in most places differential equation is taught after calculus 3. If you are familiar with differential equations, first order differential equations solving, if the equations are exact and you want to find a solution, we kind of, this method overlaps with that. Okay, so fx is gonna be 3 plus 2xy. So when you integrate both sides with respect to x, what do you get? You get f is gonna be integral 3 dx plus integral 2xy dx. Okay, so your f is gonna be 3x plus 2y is treated as constant. Integral of x is x squared over 2 plus, you get a constant, right? But there is another function, it is a function of y as well, so you would get something like h of y. You see, remember that it's not, if it was just a one variable, then you would have got a constant, but there is another variable y and you are integrating with respect to x, so that's what it is. So f is going to be 3x plus, 2 gets cancelled out, so you get x squared y plus h of y. Now just for fun, if you differentiate fx, derivative of 3x is 3, derivative of x squared y is going to be 2xy, plus h of y is treated as a constant because there is no x involved in it, so this would go to 0. Do you see that? So instead of that, that's what it's okay. But then you can find, your goal is to find h of y. How do I find, your goal is to find h of y. Now, how do I find h of y, right? So how do I find h of y? I'm going to make use of my Clay-Root's theorem and fy here. So I'm going to find fy. So when I differentiate 3x with respect to y, I get 0. When I differentiate x squared y, I get x squared, plus when I differentiate this with respect to y, I get h prime y, and I'm going to set it equal to q, and that is nothing but x squared minus 3y squared. So that means you get what? You get x squared plus h prime of y is going to be x squared minus 3y squared. So these two gets cancelled out, so you get h prime y is going to be negative 3y squared. So integrating both sides with respect to y, we get, you get hy is going to be integral of negative 3y squared dy. So that's going to be negative 3 times y cubed over 3 plus k. This time I'm writing k because I have already accounted for another variable. So h of y is going to be negative y cubed plus k, right? So that means I want to substitute that, where is my h? I'm going to substitute that here. So when I substitute that in there, you get f of xy is going to be, what is that, 3x plus x squared y minus y cubed plus k. So because it is because your function was a conservative vector field, which we showed in the previous slide, I'm able to find a potential function, that one. Now, is this right? Is my answer right? Check. I'm done with the problem, but I just want to check and show you that. If I find fx, what do I get? I get 3 plus, I get 2xy, which is the same as this one. Then if I find fy, then I'm going to get, this is derivative of this with respect to y 0, and derivative of that is x squared minus 3y squared. Derivative of y cubed is 3y squared, which is the same as the q component. So we know that the gradient of f is nothing but the conservative vector field f. So if f is a conservative vector field, then you can find this. And we found this. Now you may ask me, why am I interested in finding such a thing? Because I want to find a line integral, okay? So that means if I want to find a line integral f dot dr, I know this is a conservative vector field, so I can write this as gradient f dot dr. Alright, so this is going to be integral gradient of f dot r prime of t dt, where your t is from 0 to pi. So you need, if your vector field is conservative, you can find a potential function. If you can find a potential function, you can use fundamental theorem of calculus, right? So that means using fundamental theorem of calculus for line integrals, this is nothing but f of r of pi minus f of r of 0. I hope you understand that. Again, because f is a conservative vector field, I'm able to go from here to here, and this is just a definition of a line integral. There are several ways you can write a line integral, so that is that. And because I'm able to write like that, because by using the fundamental theorem of calculus, I'm able to write that. So if I don't have the fundamental theorem of calculus, I will still be able to do it using the concept that I learned in 16.2, but it will not be that easy. That's all. So now, what is r of pi? Remember that r of pi is going to be e to the pi sine pi e to the pi in cosine pi, okay, and that's going to be sine pi is going to be 0, so this is going to be 0, so that's going to be 0 in negative e to the pi, okay. Now what is r of 0? R of 0 is going to be, you're going to write e to the 0 sine 0 and e to the 0 cosine 0, so that's going to be sine 0 is again 0, so that's going to be 0 and 1, okay. So that means it's going to be by using fundamental theorem of calculus, if it's going to be f of 0 negative e to the pi and f of 0 minus, sorry, f of 0 1, okay. So that's going to be, now what is the function f? You know the function f from the previous thing, we did all that and found out that. So your function, recall that f of xy from the previous problem was what, 3x plus xy x squared y minus y cubed and plus k, doesn't matter. So what do you get? I mean, x is 0, when you put x as 0, you get 3 times 0 plus x is 0 squared, y is e to the pi, okay, negative e to the pi minus y cubed is negative e to the pi cubed plus k here, that's going to be your first thing, minus, you're going to put f of 0 1, so that's going to be 3 times 0 plus 0 squared times 1 minus 1 cube plus k, okay. So that's gonna, what does that give you? That gives you, remember we are calculating f dot dr, right, line integral over there. That gives you, this is a 0, this is a 0, this is gonna be e to the 3 pi plus k, this is a 0, this is a 0, minus 1, okay, minus times minus is plus 1, minus times k is negative k. So that's going to be e to the 3 pi plus 1. So that's what is a line integral. Now you might think, okay, remember that because this was a conservative vector field, I could write this as gradient of f dot dr. So that's going to be, upon transforming the limit, you get f of gradient f of r of t dot r prime of t dt, and upon substituting the limit you get that. You might think, why am I interested in doing that? It is like, let's say this is nothing but this is the definition for work. Let's say if you are interested in, if your force is given by this and or a conservative vector field, right? If your force on the object is given by this and you're moving an object along this path from 0 to pi, then, if, okay, recall, f is, what is that, you got 3 plus 2xy and x squared minus 3 y squared, right? Are you with me, man? So if you're applying a force equal to that in moving an object along this path from 0 to pi, what is the work done? The work done is this many units. So this has a really physical meaning to it. Now if this was not a conservative vector field, I could not have used fundamental theorem for line integrals. If I did not use a fundamental theorem for line integrals, then the evaluation would not have been this simple. It would have been far more difficult using the problems that we have done in the section 16.2. okay, I hope this is clear. This ended up being a long lecture, but I hope you enjoyed it. Stay safe, stay healthy, and I'll see you again. Bye bye.